Recommendations for electronic circuits prototyping. Use a 30-watt soldering iron to solder your component in your board. Use a soldering iron and sponge with water to clean the tip of the soldering iron. Use a good quality soldering wire to wire up your prototypes. Use a proper wire wrapping wire to wire up your prototypes. Use soldering fume extractor to protect yourself from the fumes of the soldering wire. Use a good quality tin-coated wearer board for your prototyping. In our previous session, we have developed a circuit of PT100 amplifier, and we have interfaced this circuit with pin number 5 of this microcontroller, which is analog input 3 of this microcontroller. And we have calibrated the PT100 amplifier circuit from 0 to 500 degrees centigrade, and we have observed in previous session that the voltages at 500 degrees centigrade are 4.86. Here we have connected a 200 watt lamp with trike control circuit. Here we can see a trike control circuit composed of a trike and MOC3022, that is optically isolated trike. And here we have the zero crossing input circuit to get reference of the AC sine wave, and on the basis of zero crossing input signal we can control the fire angle of the AC power which is connected to this 200 watt lamp. We can control the AC voltages which are connected with this 200 watt lamp. We have connected a 200 watt lamp with this fire angle control circuit, and we have developed a program to control the voltages across this lamp with the help of these switches. And here we can find our project, that is fire angle control project. In this project we have developed a code to control the voltages across 200 watt lamp. In this session we will write a program to get the temperature feedback of surface temperature of the lamp. And here we have installed the PT100 sensor near to this lamp, and we'll get the temperature feedback of the surface of this lamp in our circuit. Here we have connected PT100 sensor with our PT100 amplifier circuit. First we'll measure the temperature in terms of voltages at this test point. Then we'll display the temperature on LCD display by converting these voltages into the temperature. As we have observed in our previous session that the voltages at 0 degrees centigrade were 0 volt. So here we can write that is 0 degrees centigrade equals to 0 volts. And for 500 degrees centigrade the voltages were 4.86. That is at 500 degrees centigrade the voltages were 4.86 volts. As the relation between voltages and temperature is linear, so we can establish a relation between temperature and voltages for 1 degree centigrade. As we know that 4.86 volts corresponds to the temperature, that is 500 degrees centigrade. It means 1 volts will correspond to the temperature, that is 500 degrees centigrade, divided by 4.86, which is equals to 102.88 degrees centigrade. Now we can find the temperature corresponds to 5 volt, that is 5 volts multiplied by 102.88 degrees centigrade equals to 514.4 degrees centigrade. As we have calculated that 102.88 degrees centigrade corresponds to the 1 volt, now we can check the temperature in terms of voltages on our prototype. Now we'll check the temperature in terms of voltages at the output of our PT100 amplifier. Here we can check we are getting 0.25 volts at the output of our PT100 amplifier. Now we'll convert these voltages into temperature. Now if we'll multiply, that is 102.88 degrees centigrade by 0.25, the voltages we are getting at the output of our PT100 amplifier equals to 25.72. It means that the temperature of the room is at 25.72 degrees centigrade. Now we'll increase the voltages across this lamp with the help of these switches, and we'll measure the temperature feedback with the help of this PT100 sensor and the PT100 amplifier which we have developed in our previous session. Now we'll increase the voltages across this lamp by pressing switch 1. Here we can check we have applied a small power to the lamp. Now we'll measure the temperature feedback at the output of our PT100 amplifier. And here we can check the voltages at the output of PT100 amplifiers are 0.29 volt. Now the voltages are 0.3 volt, 0.31, 0.32. If we'll increase the voltages across this lamp further. Now we'll measure the temperature in terms of voltages at the output of PT100 amplifier. Here we can check the voltages are changing very rapidly. Okay, now we'll decrease the voltages across this lamp using switch 2. Here we have checked if we'll increase the voltages across this lamp, the surface temperature of the lamp will increase and we'll get the feedback of the surface temperature with the help of this PT100 sensor. Now we'll display these voltages in terms of temperature on LCD display. As we have discussed in the session of ADC conversion, that PIC microcontroller, that is PIC 16F877A, converts the 5 volts into a digital number which is equals to 1023. It means that ADC conversion in PIC microcontroller is of 10 bit. Now we can establish a relation between the digital converted number and the surface temperature of the lamp. As we have calculated, if the output of PT100 amplifier circuit will be 5 volt, then the temperature will be 514.4 degrees centigrade. Now we can relate this conversion with digital number, and we can write that the number, that is 1023, corresponds to the temperature, that is 514.4 degrees centigrade. Now we can write the conversion for unit change, that is for one number the temperature will be 514.4 divided by 1023, which is equals to 0.503 degrees centigrade. Now we can convert the number from ADC of PIC microcontroller to the temperature by multiplying the number with a constant, that is 0.503. So we can write, if we are getting number that is X from the ADC, then we can multiply this number by 0.503 to get the actual temperature in degree centigrade. Now we'll write a program to display the temperature value on LCD display after reading the analog voltages from ADC channel. Now we'll insert the LCD display in our prototype. And now we'll develop a program to display the temperature on this LCD display. And here we have our previously written program for fire angle control. Now I'll modify this program to display the temperature value on LCD display. Here we can see we have already initialized the ADCON1 register, and by setting the value of these bits, that is PCFG0, PCFG1, PCFG2 and PCFG3, if we'll set the value, that is 02 to these bits, then 3 channels, that is AN5, AN6 and AN7 will be digital input output, and from analog 0 to analog 4 all pins will be analog input. So here we have assigned the value, that is 02 to ADCON register. Now we'll go to the help, and in MikroC Pro for PIC libraries we'll go to the LCD library, and here we can find a sample program that how to initialize the LCD display. We'll copy these lines from this sample program and we'll paste these lines in our assignment section. Here we have our port assignment section. Here we will add another section, that is LCD assignments. Now we'll copy the LCD display assignments here, Ctrl V, and here we have initialized the LCD connection module. Now we'll go to the MikroE libraries. In system libraries, we'll select ADC library and we'll select LCD library, and here in our previous program we were calling just one routine, that is fire angle control routine. Now we'll call some other subroutines, that is ADC read routine and LCD display routine, and here we will write ADC_RD. Here we are calling another subroutine, that is ADC read routine, and we'll call another subroutine, that is LCD print routine. So we'll write LCD_PRNT. Now we'll write ADC read routine before main program. So here we will write, and here we'll write the ADC read routine. So we'll write void ADC_RD, and we'll write the ADC read routine between these two braces. We'll also define a variable to read the ADC value from the analog channel. So here in variable assignments, we'll define unsigned integer temp reg equals to 0. We'll read the analog channel in temperature register. We'll also define 3 more variables for temperature display, that is unsigned character, unit temperature, unit temp equals to 0, unsigned character 10 place digit for temperature display, that is 10 temp equals to 0. Now we'll define another variable, that is 100 place digit for temperature display. So we'll write unsigned character HUN temp equals to 0, that is 100 place digit for temperature display. Now we'll go to the help, and in MikroC for pick libraries we'll go for ADC library, and here we can find library routines, that is ADC initialize, ADC initialize advanced, ADC get sample, ADC read. We'll use these two routines, that is ADC initialize and ADC read, and here we'll initialize the ADC module, that is ADC underscore initialization. Now we'll write the ADC read routine. Now we'll read the analog voltages from analog channel 3. So we'll write temp reg equals to ADC read channel 3. So this command will read the channel 3 of ADC and will move the value to the temperature register. After reading ADC channel, we'll call another subroutine, that is calculation routine. So here we'll write calculation routine, and we'll call the calculation routine before main program. And here we will write the calculation routine, that is void calculation routine, and we'll write the calculation routine between these two braces. And here we will write HUN temp, that is 100 digit of temperature display, equals to temp reg divided by 100, and we'll also adjust the decimal place, that is %10. Now we'll move the value to the 10 place digit on LCD display. So we'll write 10 temp equals to temp underscore reg divided by 10, and we'll also adjust the decimal place, that is %10. Now we'll move the value to the unit place digit, and we'll write unit temp equals to temp reg %10. So here we have moved the value in 3 registers, that is 100 place digit for temperature display, 10 place digit for temperature display, and unit place digit for temperature display. Now we'll display these numbers on LCD display in LCD print routine. We'll also print some initialization text on LCD display. So we'll go to the help, and in LCD library, here we can check from the sample program that we have to initialize the LCD before while loop. So we'll copy this command from here, Control C, and we'll paste the LCD initialization command here, Control V. We'll also copy these two commands from sample program, that is Control C, and we'll paste these lines here, Control V. And here we can find that how to define a text array. We'll copy this assignment from here, Control C, and we'll paste the text assignments here, Control V. Now I'll modify this text as per our program. So here we'll write that is temperature feedback, and we'll print this text on first row and first column of LCD display. So here before while loop will print the initialization text on LCD display, and here from sample program we can check that how to print the text on LCD display. We'll copy this command from here and we'll paste the line here in our program. Here we can see we have defined our text by text1. So here we have passed the variable that is text1 to the LCD out command. Here we can see from this command that we are printing text1 on row 1 and column 1. Now we'll print the temperature value on second row of the LCD, and we'll print the temperature value in LCD print routine. So first we'll correct this name, that is LCD print, and we'll write the LCD print routine before main program. So here we'll write, and here we'll write the LCD print routine, that is void LCD print, and we'll write the LCD print routine between these two braces. To print the characters on LCD display, we'll use this prototype, that is LCD character, character row, character column and character, and here we'll write that is LCD underscore character, and here we'll write another text assignment to display the temperature on LCD display. So we'll copy this assignment from here, Control C, and we'll paste it here, Control V, and we'll change the name, that is text2, and we'll modify this text accordingly, that is degree Celsius, and here we'll also define the places for unit, 10 and 100 place digit, that is TTT, that is temperature. Now we'll adjust the length to 20 characters. Now we can count the positions for unit, 10 and 100 place digits, that is 1, 2, 3, 4, 5, 6, 7. It means that we'll print the unit place digit on 7th column, 10th place digit on 6th column, and 100 place digit on 5th column. Now here we'll define the row, that is 2, and column will be 7, and the character will be unit place digit, that is unit temp. Control C and Control V. To print this number on LCD display, we have to convert this number into ASCII equivalent, and from tools we can go to ASCII chart, and here we can see the equivalent ASCII for 0 is 48. So here we'll add 48 to this number. Now we'll print 10 place digit on LCD display. So we'll write LCD character, row will be 2 and column will be 6 and character will be 10 temp. Control C and we'll paste it here, Control V, plus 48. Now we'll print 100 place digit on LCD display, that is LCD character, row will be 2, column will be 5 and character will be 100 temp. Plus 48, and from the schematic we can check that we have connected zero crossing input to RE0, that is analog 5, and here we can check that we have assigned the value, that is 2 to ADCON1 register. Now if we'll read any ADC channel, the value of ADCON1 register will be lost, so we have to reinitialize ADCON1 register in our program, and here in ADC read routine we will reinitialize the value of ADCON1 register. So here we will write, we'll copy this line from here and we'll paste it here, Control V, and if we will not reinitialize the value of ADCON1 register, then the port, that is RE0, will no more as digital input port and will not be able to read the zero crossing input at this port. That's why we have reinitialized the value of ADCON1 register after reading the analog channel. Now here we'll print the second text on LCD display. That is, we'll copy this command from here, Ctrl C, and we'll paste it here, Ctrl V, and we'll modify the line accordingly. That is row 2, column 1 and text 2. Now here in ADC routine we'll convert this number into temperature and we'll multiply the number by 0.503. So we'll multiply the ADC read value by 0.503. So we'll write 0.503. But before compiling and downloading our program to the microcontroller, we'll modify our ADC read routine to read the analog channel after a delay of 1 second. And here we can check we have moved the value that is 02 to ADCON1 register, and we have moved the value that is 225 to the timer 0, and we are calling an interrupt service routine with a frequency of 10 kHz, and we know that the time for 10 kHz is 0.1 millisecond. Here we have the interrupt service routine which we are calling after a delay of 0.1 millisecond. So if we'll increment a variable in this interrupt service routine, and if the value of that variable will reach to 10,000, it will produce a delay of 1 second. So now we'll declare a variable to get the time of 1 second, and here in our variable assignment we'll declare a new variable, that is unsigned integer ADC delay register equals to 0. Now we'll increment this variable in our interrupt service routine. So we'll copy this variable from here, that is Ctrl C, and we'll paste this variable here, Ctrl V. Here we have incremented this variable in our interrupt service routine. Now we'll use this variable in our ADC read routine. And in ADC read routine, we'll check the value of this variable. If the value of variable will reach to 10,000, it will give us a delay of 1 second. So here we will write if Ctrl V, that is ADC delay register, if it is greater than or equals to 10,000, then our program will come into this if condition. And if the value of ADC delay register will be greater than 10,000, then our program will come into this if statement and it will read the value of ADC channel 3. And here we have converted the raw data from ADC into the temperature by multiplying it with 0.503. And here we are initializing the ADCON1 register and we are moving the value that is 02 to ADCON1. Now we'll reset the value of ADC delay register here, that is Ctrl V, equals to 0, and here we have cleared the value of ADC delay register. It means that this if condition will be executed after every 1 second. Now we'll compile the program and we'll observe the result on our prototype. Our program is compiled successfully. Now we'll power up the prototype and we'll validate our program. Here we can check the room temperature is 22 degrees Celsius. Now we'll increase the voltages across this lamp with the help of switch 1 so that we can increase the surface temperature of this lamp. Now we'll observe the change in temperature. Here we can check the temperature is increasing. And now we'll increase the voltages across this lamp further. Now we'll observe the surface temperature of this lamp will increase very fast. Here we can check the temperature is increasing very fast. And if we'll increase the voltages across this lamp further, now we can observe the change in temperature. Now we'll decrease the voltages across this lamp using switch 2. In this session we have observed that how to read a temperature feedback from PT100 sensor. We have developed a PT100 amplifier and we have interfaced this PT100 amplifier with microcontroller, and we have displayed the value of the temperature on LCD display.